Okay, so now that we've talked about currying, we're going to move on and talk about sequences. Okay, so here's the idea. A sequence is an ordered collection of elements. So conceptually, a sequence is like, there's the number 4, then there's the number 3, then there's the number 7, then there's the number 1, then there's the number 2. Okay, so like by ordered, I don't mean that it's sorted in sorted order or something like that. I just mean it's a bunch of things in a specific order. And so we've seen many different ways of thinking about sequences so far this semester. So we saw lists, right? I could have the list 5, 3, 7, 1, 2. That's a way of representing the collection of elements 5, 3, 7, 1, 2 in an order. We've also seen things like trees. So for example, maybe I have a node that has a node, and that inner node has a leaf with 5, and then a leaf with 3, and then next to that, there's a node that has a leaf with 7, and a leaf with 1, and all of that's inside of a node that has its other child, a node with a leaf with 1 and a leaf with 2. Okay, so in terms of the homework, the tree data type that you're working on using for the homework for this week, right, I could represent that same ordered collection of elements as a tree with nodes like that and leaves. We've also seen trees with data at the nodes of the tree rather than just at the leaves. So I could have like a node with, as its child, a node with a leaf of 5, and then a 3 in the middle, and then a leaf of 7, and on the other side, a node with a leaf of 1, and then a 2 in the middle, and then, I don't know, an empty over on the other side or something like that. Okay, so point being that there are different implementations of this idea of an ordered collection of elements. And the reason that we care about there being different implementations of this idea is that the different implementations have different running time. So for example, if we think about the operation of mapping a constant time function, like map of curry dad of 4 from the previous segment, something like that, right? So if I'm doing a map and the thing I'm doing to each element is constant time, then for lists, the work and span are both linear time because I go through each element of the list and apply a constant time function to it. So I get n length, where n is the length of the list, n constants. For trees, if you think about the map that you're writing for homework, what I'd expect is you get that the work is still linear, so that's good because it's less efficient to on trees, but the span is now order log it. And the reason for that is that the code you're writing for map on the homework, if the tree is balanced at least, will be making 2 recursive calls that can be processed in parallel, so the span will just be proportional to the depth of the tree, which if the tree is balanced is log of the size of the tree. Okay, so that's kind of 2 different costs for the same operation there, right? There's two different lists and trees, both represent an ordered sequence of things that can represent the same data like that or like that, but doing an operation on them can cost different things, different amounts of time. Okay, so what we're going to be doing this week is to go from what we could do with trees, which is, you might call binary parallelism. So with trees, you make two recursive calls on the two subtrees, which means that you can do two things at once. But conceptually, if I want to map the add for function on the sequence five, 3, 7, 1, 2, there is no actual data dependency between the different plus fours, right? Like conceptually, what you want to think about this is, well, I run 5 plus 4, and I run 3 plus 4, and I run 7 plus 4, and I run 1 plus 4, and I run 2 plus 4, and these might as well all happen at once, because why not? Right? Like to compute 5 plus 4, I don't need to know the answer of 3 plus 4. To compute 7 plus 4, I don't need to know any of the other answers. To compute 1 plus 4, I don't need to know any of the other answers. It's 2 plus 4, I don't need to know any of the other answers. So I might as well just do it all in parallel. But lists give you order n overhead for the span for the recursion through the list that goes element by element one at a time and does the plus 4. And trees still give you some overhead, even though it's pretty small, because, well, I can't yet talk about it, but if you think about your solution, if you've done this test on the homework already, then when you write your code for the homework, presumably there's going to be some recursion over the tree, and that recursion of the tree is going to divide into two subproblems, and so there'll be this kind of log n kind of way of doing things, log n span way of doing things. So really though, the linear or log span is coming not from the structure of the actual problem, but from the data structure we've chosen to represent an ordered collection of elements. So for this week, what we're going to be talking about is parallel sequences, and the idea is that we'll think of them as being implemented by an array with n-way parallelism. So if you've seen arrays in your 211 or in your previous coding experience, then like think that we're implementing an ordered collection of elements by an array. If you haven't seen it, that's okay. You don't really need to know what's going on under the hood. You can just program with the high-level model that we'll talk about today. Okay, so that's kind of conceptually what's going on here. So in terms of what it looks like to program with these, basically what I'm going to do is I'm going to write out some of the functions that we have available to us and at a high level what they do. So won't really be code yet. It'll just be kind of a sketch of what's going on. So when you have a sequence, there's going to be a type a_seq.seq, which you can think of as a list being like a list or a tree or something like that. So the type a_seq.seq, what you want to do is you want to think of it as an ordered collection of elements, but you don't know exactly what the sequence type is. It's going to be an unknown or abstract type where we're just going to work with it via the operations that I'll define below. Okay, so we're just going to say, like, here are a bunch of functions on sequences, go crazy and use them. And for each function, what we're going to do is we're going to say what it does at an abstract level and then what its work and span are. Okay, so let's start out with some easy ones. So there's going to be a function length that takes a sequence, and all these sequence functions get prefixed with the word seq. So there's going to be a function seq.length that takes a sequence and gives you its int. And the behavior of this length function is that if you say seq.length of the conceptual sequence x0, x1, x2, ... x n minus 1, then that's going to be equal to the number n. And the running time, the work and span, are both going to be order 1. So they're both going to be constant time. Okay, so what does it look like to use this? Well, to actually get any sequences, there's a sort of off-the-books operation that you're not really supposed to use in any code, but we can use for testing, which is you can do seq.fromList to turn a list into a sequence, and that's handy for just writing things down. So if I do that to get a particular sequence, then and then I ask for its length, then, well, that sequence has 5 things in it, that sequence has 4 things in it, and so you can see that length is computing the length. Okay, so nothing fancy going on there. Next operation, there's going to be operation seq.nth, which is going to be a curried function that takes an int to a sequence to an a. And the idea is that the behavior is that seq.nth of our kind of generic sequence here of x1, x0, x1, x2, all the way up through xn minus 1. Well, if you ask for the ith element of that, then that's either going to be xi if 0 is less than or equal to I is less than the length of the sequence, which is in this case n. Or it'll raise an exception called range otherwise, which is to say it'll crash in a specified way if you ask for something that's out of bounds. Okay, so for example, if we ask for the 0th element of that, we get 1. If we ask for the first element, we get 2. If we get for the 2th element, we get 3. 3rd element, we get 4. 4th element, well, okay. There is no element numbered 4 because the numbers start at 0. So if I ask for the 4th element, then it raises an exception range, which is saying I crashed because it didn't have a 4th element. Okay, so what this is doing is it's going through the sequence and giving you a particular element, right? So like, if instead my sequence was A, B, C, then nth of 0 is the first element, nth of 1 is the second element, nth of 2 is the third element, and nth of 3 is now out of bounds. Okay, so the idea with nth is that it gives you access to particular elements. And the fun thing, if you have seen arrays before, is that for lists, getting a particular element was a linear time operation. For trees, right, think about like the take and drop that you did in the homework, getting a particular element was a log time operation. For arrays, which is how we're thinking about sequences as being implemented, it's going to be a constant time operation. So you just sort of think of it as accessing a particular point in memory, which takes constant time. Okay, so that's ways to get at particular elements. The next thing, oh, and I should note, so nth is curried, right? So that this type here is one of these curried types that we talked about in the last segment. So it's equivalent to saying nth is a function that takes an integer and returns a function of sequences to numbers. So the parentheses go there if you leave them out. And the kind of reason that it's done that way is that, like, you can think of seq.nth of 5 as itself being a function from sequences to elements, and you can use seq.nth of 5 in different places. So if I define f to be seq.nth of 5, then I can do things like write f of that plus f of that, right? So I'm using the same seq.nth of 5 in multiple places by saying f is the result of partially applying nth to just the 5, leaving it waiting for its list input still coming later. And so then I can use that same projection of the fifth element on multiple different inputs at once. Okay, so next up, we've got map. So just like we talked about last time, map is going to take an A to B to an A sequence to a B sequence. And then the behavior is, well, it does map, right? So if you do map of F on the sequence there, then what that computes is conceptually the result of doing F on X0, F on X1, F on X2, finally ending with F on X n minus 1. Okay, so no surprise. If I do seq.map of fnx goes to x plus 4 on the sequence 1, 2, 3, then I go through and get 5, 6, 7. Okay, there's another off-the-book secret operation that you're never supposed to use in a real program, just use it for testing, called toList, which turns a sequence back into a list. And you can use that to print things out. So if I take 1, 2, 3, add 4 to each element, then I get 5, 6, 7. Okay, so no surprise about what it's doing. The thing that's different than what we talked about with lists and with trees is that the work is if f is constant time, order n, the span is order 1 if f is constant time. So unlike lists where the span of a map was linear if the function was constant time, or trees where the span of a map was log if the function is constant time, here the span is going to be order 1 because what we're thinking of sequences of is a parallel array implementation where to do a map, you really just do all n of these calculations in parallel. So with what we've done so far with pairs and recursion and trees, we've been able to do 2 things at once, which then spawn 2 more things and 2 more things and 2 more things. Think about all those tree method kinds of pictures from before. What we couldn't do is from one point in the computation decide that what I'd really like to do right now is to do these 12 sub-goals all in parallel without some overhead for dividing it up 2 by 2 by 2 by 2 or 3 by 3 by 3 or by 3 or for some fixed factor. And so the thing that sequences will let us do that we haven't been able to do before is exactly that kind of n-ary stuff. Okay, so that's kind of the conceptual kind of thing with map for sequences.